In medical imaging, aligning brain scans from different modalities, like T1 weighted and T2 weighted MRI, is one of the most fundamental challenges in computational anatomy. Why? Because these scans capture different physical properties of tissue. One emphasizes gray matter contrast, the other white matter and fluid. The intensity patterns don't match. And yet, we need them aligned to study brain atrophy, track neurodegenerative disease progression, or build population atlases. Traditional methods rely on similarity metrics like mutual information, great in theory, but brittle in practice. They fail when intensity distributions differ drastically across modalities. Worse, many modern deep learning approaches assume access to massive labeled datasets, which simply aren't available for rare disease cohorts or novel imaging protocols. What if we could design a registration method that's accurate, robust to modality shifts, requires no training data, and still achieves high fidelity even under large deformations? This is exactly what our work introduces. A multimodal diffeomorphic registration framework using neural ordinary differential equations, powered by modality-agnostic structural descriptors. Let's unpack this step by step. First, what does diffeomorphic registration mean? It means we're not just warping one image to another. We're computing a smooth, invertible transformation that preserves topology. No folding, no tearing. Every voxel has a unique inverse mapping. This is essential for downstream tasks like atlas building, segmentation, or longitudinal analysis. But here's the catch. Estimating such a transformation is an ill-posed, non-convex optimization problem. The deformation field must balance two competing goals, minimizing image dissimilarity while ensuring smoothness and invertibility. Enter Neural ODEs. Instead of discretizing time with a fixed number of steps, we model the velocity field as a continuous time dynamical system, a neural network that evolves over time. This allows us to integrate the flow using adaptive ODE solvers, achieving high accuracy with fewer evaluations. But how do we define similarity between two images when their intensities don't correlate? That's where structural descriptors come in. We explore three variants. First, the classic mind descriptor, modality-independent neighborhood descriptor. It computes self-similarity in local neighborhoods, measuring how similar a patch is to its neighbors across space. Because it depends on local structure, not absolute intensity, it's naturally robust to modality shifts. Second, we use contrastive learning to train a deep neural network to generate dense, self-similar feature maps. These are learned representations that encode local geometry, texture, and edge patterns, again, independent of image intensity. The network is trained on augmented versions of the same scan, learning to recognize anatomical consistency despite artificial intensity shifts. Third, we compare against local mutual information, a classic information theoretic measure. But instead of using raw intensities, we compute MI within small patches, making it more sensitive to local structure. Now here's the key innovation. We don't just use these descriptors as features. We embed them directly into the loss function of the neural ODE. The network learns to minimize the distance between structural representations of the moving and fixed images, while the deformation remains diffeomorphic. And because we use the optimize then discretize approach, we can backpropagate through the ODE flow using adjoint methods. This gives us gradients for the entire system, velocity field, descriptors, and regularization, all in one go. We evaluate on two large real-world datasets, OASIS 3 and IXI. OASIS 3 includes patients with varying degrees of Alzheimer's, from healthy to severe dementia, so we have scans with massive atrophy. IXI contains only healthy subjects, offering a benchmark for small deformations. We test across three experimental setups. T1 right arrow T2 on OASIS 3, large deformation, pathological. T1 right arrow T2 across OASIS 3 and IXI, domain shift. T1 right arrow T2 on IXI, small deformation, healthy. And we compare against state-of-the-art methods, classical ones like ANTS and NiftyReg, and modern learning-based approaches like SynthMorph, Transmatch, Multigrad Icon, ConvexAtom, and DinoReg. The results? Overwhelmingly positive. Our method with mind descriptors outperforms all baselines, by a wide margin, in dice score across all experiments. In the OASIS 3 to OASIS 3 case, we beat SynthMorph and Multigrad Icon by over 2% in mean dice, with statistically significant improvement, p. 0.005. Even more impressively, when we test on the more challenging cross-dataset setup, OASIS 3 to IXI, our method maintains superiority, proving its robustness to domain shift. But why does mind win? Because it's not just a feature. It's a geometric prior. By encoding local self-similarity, it captures the intrinsic structure of brain anatomy, cortical folds, ventricular boundaries, white matter tracts, regardless of whether the image is T1 or T2. The contrastive learning approach, while powerful, introduces additional complexity and noise. And local mutual information, though intuitive, struggles with high-frequency variations and fails to capture texture. Now, what about regularization? One of the biggest concerns in diffeomorphic registration is negative Jacobian determinants, where the transformation folds the space, violating invertibility. Most methods use penalty terms to discourage this. We analyze this by varying the barrier parameter epsilon in our Jacobian penalty. Surprisingly, even when we impose the strictest constraints, forcing det, J, 0 everywhere, our method maintains excellent accuracy. In fact, the median dice score remains stable across epsilon values, while other methods like synthmorph degrade. This shows that our framework is not just accurate, it's robust to explicit regularization. It can adapt to different levels of smoothness without sacrificing performance. And efficiency. Our method runs in about 67 seconds per pair on a single GPU, faster than many learning-based models. The contrastive variant takes longer, 130 seconds, because it requires inference on a frozen feature network at every optimization step. But the extra time doesn't translate to better results. Mined features, with their simplicity and interpretability, deliver the best trade-off. So what makes this work special? First, it's instance-specific. No training required. You give it a pair of images, and it registers them. No need for a pre-trained model or large dataset. Second, it's modality-agnostic by design. It doesn't assume intensity correlation. It works on any pair of MRI sequences, or even across different imaging systems. Third, it's scalable. It performs well on both large deformations, like those in Alzheimer's, and small ones, like in healthy subjects. And fourth, it's theoretically grounded. By using neural ODEs within a PDE-constrained variational framework, we maintain the mathematical rigor of large deformation diffeomorphic metric mapping, while gaining the flexibility of deep learning. This isn't just a new registration algorithm. It's a new paradigm, learning-free, structure-driven, continuous deformation modeling. We believe this approach opens the door to reliable multimodal registration in clinical settings where data is scarce, protocols vary, and high accuracy is non-negotiable. Future work. We're exploring extensions to dynamic imaging, like fMRI or time-lapse CT, where the same anatomical structure evolves over time. And we're investigating how these structural descriptors can be used to build domain-invariant atlases across scanners and hospitals. In short, if you're working in medical image registration, and you're tired of models that fail on new modalities or require endless training data, this is the direction to explore. Because the future of registration isn't in more data. It's in smarter priors.